Hello everyone and welcome to the 6th tutorial video on Fusion 360. This time we will be looking at how you can create a rocket nozzle. As you can see here, this is an example that I made some time ago. This is the LE7 engine, which is used on the first stage of JAXA's H2A and H2B rockets. As you can see, it's made up of some components, and if we remove everything like the pumps and all the plumbing, then eventually we just have the throat and the bell shape. Like in this case it was a bell nozzle, but for this tutorial we will be making a conical nozzle, as it is a bit easier, and especially for like people who will make rockets themselves, if it's their first rocket they will go with a conical nozzle as it is easier to manufacture. But either way, if you want to create it for your model, you can just use a function such as the square root of x to create the bell-shaped nozzle. Okay, so let's just turn everything back on. Yes, let's go to courses and let's start with our rocket nozzle. So first of all, we will create a sketch that we will resolve around a certain axis, so you can choose which one, but for this case I'm going to choose the y-axis. Okay, then let's go to the Modify tab, change parameters, and create some user parameters such as the throat diameter, and let's say in this case it's 10 millimeters. Okay, then the diameter of the combustion chamber, let's say 50 millimeters. Yes. Let's take it a bit bigger. Let's say 80. Yeah, seems like a good value. Then let's say the exit diameter. Let's take this one as 50. Okay. Got these. Yes. Okay. Let's go to the front plane. Lock our gimbal. Okay. And let's now just sketch the basic geometry of our conical nozzle, just like that. Make our origin visible so that we can place dimensions on it. Let's start with our throat, as it is the smallest dimension. So this one equals the throat divided by 2. And use the constraints to fix this one on the x-axis. The combustion chamber diameter was dc divided by 2, just like that. And then the exit diameter, de divided by 2, just like that. And then now let's define some angles. Let's take this angle at 50 degrees and a half angle here of, let's say, 20 degrees. But we have a nozzle that's a bit longer. Actually, let's change this one to 45 degrees. Yeah. Okay, so now we have the basic shape of our nozzle. The next thing that we can do is add a certain thickness to it. Just like that. So let's say thickness of 2 millimeters. Let's make sure it's horizontal. So 2 millimeters. Oh. Yes, just like that. And then we'll do the same at this point. 2 millimeters at an angle of 0. Yeah. Let's just do this. Okay. And let's do the same over here. 2 millimeters. Let's now connect it all, just like that. Then the next thing that we will do is revolve this, create our cutouts in it, and then create the second layer, which will cover up the regenerative cooling channels. So this will be a nozzle with regenerative cooling included as well too. Let's also just make a small flange of 12 millimeters, just like that. Okay. So yes. Finish, revolve, select everything, select our center axis. Okay. Just like that. Now we've got the basic shape of our rocket nozzle. Next thing we will do is just select the plane, and we will create the cooling channel path. So what we'll do is just, in this case I'm just going to draw a line with a certain length. Now pick the collinear, make sure it coincides with the y-axis. Now let's give it a certain length. Let's say in this case just 75, and this at a distance from the top. And I'll just change this one up because I only wanted to start from the throat, because this will be the part that needs the most intensive cooling. Okay, just like that. It's looking good. Yes. Finish the sketch. Yep. Now what we will do now is we will use the project function. So let's create a new sketch. This plane, go to create, project or include, then project to surface. Now just select your faces. So we want to project it on this face. And now let's select our curves that we've drawn. Let's place it along a vector, just like this. All we will do now is finish the sketch, go to create, then select the pipe function, go to circular. Oh no, we will do it differently because otherwise it won't have such a nice shape. So now we have this projection. We'll just leave it for a while. Now create a new sketch. Create project. I can just project the outline of our body. What we'll do now is again add a thickness of 2 millimeters. Not like this. Yes, make it horizontal. Let's do the same over here. 2. And also the same over here. 2. Okay. Let's now connect all of this just like that. And also let's create a circle of about 10 in diameter. Let's say with an inside diameter of 7. What we will do now is place it at a certain distance. Yes, like if you look, 12 seems about right. Maybe even 10 looks nice. Yes, like this is looking okay. And now this is at a fixed distance, 35 millimeters, just like that. Okay. This will be the inlet for the coolant fluid, or for your cryogenic fuel in most cases. Let's do the same over here. So let's say 10. Wow. Let's take it a bit smaller. Let's say about 8. And a diameter of 6. Okay, just like that. And now give it a nope. Yeah, this is looking. So yeah, this is looking quite good. Okay. So now that we have this, again, let's finish our sketch. Finish it. Revolve. Choose the parts that we want. Select our axis. Yep. Okay. What we'll do now is go to create pipe, select this one, and of course not select a diameter of 20, but let's say a diameter of 2. Hit OK. And now we'll go to create pattern, circular pattern, select our pipe that we just created, go to axis, select, just select circumference, and now we can choose how many cooling channels that we want to include. You could say 10, maybe 12. Yeah, so let's go with 12. And just to check if everything went alright, we can go to inspect and then choose the section analysis. Now we can just select the face. As you can see, our cooling channels have been created successfully, so that's quite good. As you can see, our cooling fluid can just flow from the throat all the way down to the exit, at which then it will return back to the injector and be injected into our combustion chamber. Okay, so that's looking okay. Let's give it some fillets. But yeah, as you can see, this is just a very basic nozzle. Like in real life you would do much more calculations, and yeah, like some features you would give much more consideration before doing it, but this is just a basic tutorial on what functions you can use to create your rocket nozzles. After this one, I'll show you some examples of projects of some rocket nozzles. Okay, so we've added some fillets, and then you would make like your inlet and your outlet. Let's say in this case, construct, let's pick an offset plane just right about here, a little bit further. Yep, so let's pick plane at 20. And now you can just create your inlet diameter. Let's say these dimensions. Just like that. At the height of 35 if I was correct. Yeah. For this case, let's 35. Of course, with the fillet, it creates like special shape. Finish it. I can go to extrude and do to object. And let's not cut it, but let's join it. Okay. Join. And again, here you can create a small fillet of 0.5 millimeters. And let's create another cutout. Just like that. So now you have your inlet where your fluid can enter your nozzle, and then you would actually do the same at your exit. Yeah. So then potentially you would do the same. So this is like how you could basically construct a nozzle, but let's just give you some examples of some nozzles. So of course here you've got the LE7 rocket nozzle. Let's go to the rocket example. And then here we've got our, no, let's not use a recovery file. So here we have a bell shape that was used for the EUROAVIA reusable rocket. And if we go and look at the sketches here, you can see in this case I used the square root of x function, or variation of the square root of x function, to create the bell shape. So then you can just plot some points, or if you want you can create an Excel and then import the points as a spline. Then again I created the return circuit for the nozzle cooling system, as you can see here. Of course here everything was created in one part, and then I added some rings and just added some detail to it. Then here the mounts for the thrust vector control system. But actually you just use the same basic function. So as you can see, you create your sketch, you use the resolve, or the revolve, excuse me, use the revolve, then you create your other sketches. Again, you can use revolve functions and so on, use circular patterns, add your tubing. So yeah, actually it's every time the same process that you apply when creating a rocket nozzle. But let's show one that was created to be cooled. We've got some, where is it? Here. Okay. Nope, it's not a test launch pad. Test samples. So this is an example of a liquid-cooled rocket nozzle. This one was 3D printed and had an electroplated coating so that the plastic could reach much higher temperatures. So as you can see, you've got an inlet, you've got an outlet. This is also immediately an assembly. And then here you can see the actual nozzle with some cooling channels that were 3D printed. And then you've got an outer jacket to cover it up. So we've got this one. And then there was also an aluminum version that was meant to be 3D printed in aluminum, so by using selective laser sintering. And here again, let's go to the analysis and look at the section. So we've got the cooling channels, and maybe you would think like, why does it have these funny angles, especially at the top? And that is because for 3D printing you need to stay below a certain angle. Otherwise, if you have an overhang that is much higher than 45 degrees, the printer could have some problems creating those cavities in your model. So that's why I tried to use this rule of don't go any steeper than 45 degrees, or don't have an overhang greater than 45 degrees, so that there was less chance of the part failing. Let's actually see if I can have a better view of it. Let's go to inspect, section analysis. Let's just put it here to show you that, as you can see, it had integrated cooling channels into it, and everything was printed in one go. Also here you can see that the inlet is solid, and this was meant to later be drilled out, as it would create some problems if it wasn't solid in the first place to be 3D printed by the metal powder. So yeah, these were some examples of rocket nozzles that you can create. I hope it was helpful, and I would say see you in the next video. I hope you've learned a lot, and if there's anything, please contact me. Yeah, and we'll see what we can do to help you. Okay, so have a good evening and goodbye.